I'm Matt Patrick. I work for Hawaiian Volcano Observatory, and Tricia Nadeau is here as well. And we'll be kind of going back and forth talking about different aspects of the summit activity. And we're here basically just to give a summary of what's been happening and kind of the recent changes over the past year. And this is a recent view from the western caldera rim showing Halema and the sections of the caldera floor that dropped during 2018 and the other levels of the caldera floor here. And this water pond that's a new feature over the past several months, or since summer. So just to give a basic overview of Kīlauea Volcano, this is probably a review for most of you. But Kīlauea is on the southeast portion of the island of Hawaii. And the summit caldera is a center of much of the historic activity. And Kīlauea has two rift zones. The southwest rift zone, which is not shown here, not labeled here, sorry. The east rift zone, which extends out along here. And there has been a large amount of historic activity, including a lot of recent activity, including the Pu'u'o eruption from 1983 to 2018. And the big 2018 eruption occurred on the lower flank of the volcano in the lower east rift zone. And of course, the lower east rift zone contributed to, or was associated with, collapse of a portion of the caldera floor here. So this is a recent view of the summit. And here we are at the visitor center. And here's the caldera a couple miles across. And we have this new scarp, this new cliff in the center of the caldera, and that formed during the subsidence of this portion of the caldera floor during 2018. And we have Halema in the southwest portion of the caldera that enlarged and it deepened during the 2018 activity. So Halema is, we're going to be talking a lot about it, and it's important to recognize that this is a sacred place, and the park has a lot of great background on the cultural context of the summit, and Halema in particular. And it's the home of Pele, and this is related to the fact that Halema has been a center has been a center of activity for many years. So there was lava lake activity through much of the 1800s into the early 1900s. Nearly continuous lava lake activity. And the lava lake activity at the summit in Halema was a big reason that HVO was founded. It was founded in 1912, and the reason that it was started was to make direct or close observations of continuous volcanic activity, to try to better understand volcanic hazards and to make better forecasts. That lava lake activity from the 1800s to basically a century of lava lake activities from the 1800s into the early 1900s came to an abrupt end in 1924 when there was explosive activity that widened the crater, ended that 100 years of lava lake activity. And through the rest of the 20th century, there was still summit activity, but it was sporadic and episodic, usually short-lived, days or weeks. And the last eruption of the 20th century was in 1982. And then there was 25 years of an eruptive pause at the summit. And lava lake activity returned in 2008. And that lava lake activity lasted for 10 years. And how many of you stood at Jagger and watched the lava lake here? Yeah? Well, most of you. Many times you could just see the glow because the lake was a little bit too low to see directly from Jagger. But there were numerous times, particularly in 2016, when the lake was high enough that you could see it on many days. So this was a really spectacular phase of activity on Kīlauea. There are not many lava lakes, persistent lava lakes on Earth. And this was one that was very accessible, provided a lot of new insight into lava lake behavior. that came to an abrupt end in 2018. So let's talk about the 2018 activity. But basically, there was a large eruption, lava flow eruption on the lower flank of the volcano, there, on the Lower East Rift Zone. And that eruption caused magma to drain from the summit magma chamber. And that removes support from the roof of the chamber, and the floor of the caldera dropped. Portions of the caldera floor dropped, causing a kind of enlargement of Halema and also subsidence of the broader area around Halema. And that ended, that 2018 activity ended the long-lived Pu'u'o eruption. 35 years of activity there ended very abruptly. And it also ended that 10-year-long lava lake that we had at the summit. There have been previous collapses at the summit, a handful in the 1800s, but the one that occurred in 2018 was the largest one that we know of in the past, that's been recorded in the past 200 years. And unfortunately, the Lower East Rift Zone eruption has the distinction of being the most destructive eruption in Hawaii in the past 200 years. Over 700 structures were destroyed. So this gives you an idea of what the Lower East Rift Zone eruption looked like. This is the dominant vent, Fissure 8. You get a sense just from the size of this channel and the rate that lava is flowing through it, that these were very high eruption rates. Eruption rates 50 to 100 times greater than what we observed during the previous years of Pu'u'o activity. And that high eruption rate was draining magma from the summit magma chamber, causing the floor of the caldera to drop. And this is a time-lapse camera that we had near Keanakakoi, looking north and showing the drop of this section. This used to be flush with this, and it dropped over 100 yards. Other sections around Halema dropped much more. To give you a sense of the topographic changes at the summit, this is what the caldera looked like before the 2018 eruption, taken in early 2018. And here we have the main caldera floor. We have Halema here, about a kilometer or 6/10 of a mile in diameter. And we have the lava lake, a few hundred yards across. These were recent overflows from 2015. And after the eruption, this is what the caldera looked like. Wow. So we had this section, this downdrop block that sank in a piston-like manner. And then we had enlargement and deepening of Halema. So I'll go back and forth here, and you get a sense of what changed. Yeah, so dramatic changes at the summit. So now, Tricia is going to talk a little bit about sulfur dioxide.
Thanks. Is my mic good? Okay. So, Matt talked about lava and the physical changes that we've seen, but especially if you live here or visit the park, you're also concerned about what the gases are doing at any given time. So let's start big picture with the SO2 emissions by year. So here's a plot since SO2 emission rates, that type of measurement started, which was in the late 70s here. So here's where Pu'u'o started erupting in 1983. And here's when that summit eruption, that lava lake began. This really high peak over here, that's the 2018 eruption. So if we look at this sort of Pu'u'o era, we had about 1 megaton per year, which is 1 million tons of sulfur dioxide per year. So that's sort of this plateau here. There's some variations, but it was relatively steady for a long time. And then that lava lake opened up at the summit, and things jumped, especially early on. It did tail off a little bit, but it was still pretty high, at least 2 million tons a year of sulfur dioxide that was being emitted. Then we hit it's not last year anymore, it's 2020 now. So 2018, 10 million tons or more of SO2 came out. And remember, the eruption wasn't even that long. It was only a few months. That wasn't the whole year. So if that had continued for a longer portion of the year, we would have been looking at a much higher peak over there. So that's obviously a record breaker in terms of Kīlauea since these kind of measurements began in the late 70s. And then, like I said, 2019 is over, so now we could total those emissions up. And we have this teeny tiny little amount that came out last year. So that's actually the lowest that we've had since the measurements started, and 2018 was the highest. So we just swung from one extreme to another within a year. And just for context, because some of you may not be from around here and you didn't experience these high SO2 emission rates. For context, the so-called dirtiest power plant in the US that emits SO2 in Ohio is not even 1 million tons a year. So that's about this red line. So even at these low emission rates, we're still on par with SO2 producing power plants. So when we do have active eruptions and active lava happening, our numbers are way more than any individual source like that. So now I'm gonna, since this talks about what's going on at the summit, I'm gonna focus, jump to 2018 and 2019 specifically. So these are emissions from during the lava lake era. They're pretty noisy, they're scattered, but they're in this thousands of tons a day range that was coming off that lava lake of sulfur dioxide. And then this light purple band here, those are the events of 2018. So you can see early on here when Kīlauea was having those ashy explosions early on in the 2018 eruption up at the summit, we did have a bit of a spike related to those ashy explosions, but pretty quick things died off. And then here's our average of about 200, 300 tons a day from before the lava lake. So like I said, lava lake was about 5,000 plus or minus a few thousand. Back before that lava lake existed, it was only a couple hundred tons a day. And so that's what that red line is. We had that for a little while, sort of in early fall of 2018. But since then, all these purple dots way down here on the bottom, we've maxed out at about 70 tons a day in these recent months. More often than not, we're in the realm of 30 tons a day, which is very, very low, given that we've had such constant activity at Kīlauea since 1983 that brought with it more SO2 than that. So why is it so low now is people's question. Well, we don't have any lava, but how is that related? So when magma is deeper, that gas, especially SO2, stays dissolved because you have more pressure on that magma and the gas can't escape. So it's like when you have a bottle of soda, when that cap is on, before you've opened it, all those bubbles are still dissolved in your liquid because that cap is keeping the pressure on that liquid and keeping the gas in solution. So that's the same thing that happens with gas and magma. When the magma is deeper, the gas stays in it. The difference between magma and a bottle of soda is that your soda only has carbon dioxide in it. Magma has a bunch of different gases and they all behave differently. So the SO2 right now, where the magma is deep enough to keep the SO2 dissolved, but carbon dioxide, that CO2, it wants to escape even at those greater depths. So we do have CO2, that carbon dioxide, currently being emitted from the summit. But there's a lot less of that SO2. That's what's mostly staying dissolved. Like I said, we do have a little bit, averaging about 30 tons a day that is coming out. But the thing about deeper magma is that you just don't have a heat source as close to the surface as you used to. So we've got cooler conditions, which means water can persist. So throw back to high school chemistry, and I see some kids here, you'll get this when you get to high school chemistry. If you take sulfur dioxide and add water to it, you're gonna get this, which is sulfuric acid, which I'll talk a little bit about more later, and hydrogen sulfide. So hydrogen sulfide is a different form of sulfur gas, and that's the one that smells like rotten eggs. So if you're a local resident, you may have noticed there's a little bit different odor in the sulfur smells now than we used to have with the VOG from the lava lake or the Pu'uo'o era. And that's because we're getting this hydrogen sulfide. And there's still not much of it, but you can detect hydrogen sulfide with your nose at much lower concentrations than you can sulfur dioxide. So even though we have a lot less of that hydrogen sulfide now, and a lot less of the sulfur gases in total, you can still detect it because it's hydrogen sulfide instead of sulfur dioxide. So it's this deeper magma and the fact that things are cooler at the surface. That's why our SO2 emissions are so low. Any that we do, a lot of what we do have, then hits water and gets converted to a different gas. So that's why the sulfur dioxide emission rates are so low. We are still constantly measuring sulfur dioxide. So we recently actually added these real-time these plots of concentration to our public web page. So you can always log in and check. There's a few different stations. This is called Sand Hill, which is about 1 kilometer downwind of the summit crater. And you'll notice these are concentrations, not emission rates. So this is just how much SO2 is in that spot at any one given time, not tons per day or anything like that. And you can see we've got a little spike here to 0.5 part per million, which, sure, that looks like the highest one on this plot. But if I had a longer plot from this station back to the lava lake era, we'd be way up past the ceiling on the 3rd floor that doesn't exist. So things are still very low in terms of concentration and emission rate of SO2. One thing that we've done recently is actually add a different kind of gas monitoring station called a multigas. So that's what this guy is over here. And this lives on the caldera rim just off Crater Rim Drive. And we added that because we now have a new focus on all the carbon dioxide that's coming out and that hydrogen sulfide that's coming out now. So instead of just SO2, this multigas can detect those other gases. So that's still a little bit in developmental mode at this point, so that's why it's not quite on the website yet, but hopefully it'll eventually get there after we work out some of the kinks in the station. So, like I said, that's sort of the state of gas right now. So now I'm gonna turn it back over to Matt to talk a little bit about our other new feature at the summit.
Okay, so this is a recent, well, this is a kind of a bird's eye view of what the summit caldera looks like today, more or less. This is taken from aerial images that we collected on December 18th. And so here we have this downdrop block from 2018, and here's Halema. And the new feature since July is this water pond. And this is the first time that a water pond like this has been observed at the summit in at least 200 years. And this is a kind of a virtual fly-through of the summit, giving you a sense of the topography. Here's the scarp that formed in 2018. This is that lower block. Other blocks that kind of subsided during the 2018 activity. Here's the deepest pit, which is Halema, and the water pond at the very deepest portion of that. This exposure here is new. It actually exposed an area that used to be called the South Sulfur Banks. And there we are. There's actually a small portion of the original Halema crater floor in this lowermost block here. So this morning, this is the view from the webcam taken from the western caldera rim. And we have Halema, we have these fumaroles. These have been pretty steady. And we have the downdrop block and then the broader caldera floor and the water pond here. And you can see it as this yellow, kind of brown, orange color. You can also see this haze, and people who live on the island can appreciate that this is, I think some water has gotten in, some moisture has gotten into the camera enclosure because of all the heavy rain. So we have to, on our to-do list is to go out there and open up the case and dry it out and put in some desiccant. So. Yeah, so this water was first observed in late July, and at that time, on this time of the overflight, it was just a tiny pond, very shallow, and it just kept rising, and it started to rise, and it has risen ever since. This is just showing the first month of rise. You can see just filling the lowermost portion of Halema here. At the start, it kind of had this kind of greenish yellow color. But yeah, every time we go out and we measure it or we look at it, it's a little bit higher than it was the previous time. And it's been showing a very steady rise rate, about 5 inches a day. No major changes in the rise rate. And currently, it is about 74 feet deep, so pretty deep. And yeah, going out there on our visits, we make these measurements with a laser rangefinder, but just with the naked eye, you can often detect, see how much it's risen just by comparing the water level along rocks along the shoreline here. So this was this kind of steady rise. At first, there was a question of whether this was just surface runoff, rainwater, or whether this was groundwater seeping in. And the fact that in this first month of activity that we observed, this level just kept rising at a relatively steady rate, regardless of rainfall amounts. So that was suggesting that this was groundwater, the kind of the broader ground water table seeping in. And this is what it looked like this morning when we went out. You can see a lot of color variation across the lake and kind of a blue-green color here in the eastern end. This is from the western caldera, so we're looking east. And you see these color variations, and Tricia will talk a lot more about how the color corresponds to the chemistry. But the size, like I said, it keeps rising every day. It keeps growing because of the flare geometry of Halema. And right now it's about 190 meters, or over 600 feet long, over almost 300 feet in the north-south direction. So this is east-west, north-south. Yeah, what we observe is that this color variation is these blue-green areas in the time-lapse videos that we take seem to be areas of influx, so maybe fresher water, surrounding water that's seeping into the lake. And then you can also see these distinct color bands here. So this is a time lapse, 2 hours of activity taken from the east, so different direction. And obviously there's a lot of steam, suggesting that the water surface is hot. And you can see the motion along the surface here. What you can't really see in this video, but you can see in others, is that these areas, these blue or green areas, seem to be areas where water is kind of migrating into the pond or flowing in. You can see a little bit of that here. Thermal images, we take thermal images of the lake from the ground and also from the air. And they've shown that the water surface temperature is between 70 and 80 degrees Celsius, or about 160 to 170 degrees Fahrenheit. Relatively consistent over the past couple months. So this is the water pond. This is hot, obviously, and heated by the magmatic system. So to give an idea of how a water pond could form in this kind of setting, this is just kind of we can go through some cartoons. It just kind of shows kind of a schematic of cross sections beneath the ground. So when we had the lava lake between 2008 and 2018, we had this large lava lake, a couple hundred meters across, and we know from when it drained that that cavity did not go down too far. It went down a few hundred meters, and then it was presumably fed or supplied by a narrow conduit, a feeder conduit from connected to the magma reservoir, the chamber. Now this is hot, obviously. This is magma. So presumably it would drive away any liquid water, and you'd have what's called a steam sleeve. We know from a well that's about a mile away on the caldera floor that the water table here is high. And after the 2018 eruption, when this area collapsed, Halema collapsed and disintegrated, presumably the water then had an opportunity once this area, these hot rocks, this area that had been heated started to cool. It gave an opportunity for water to start seeping back in. And now what we have is water kind of seeping back in, but also trying to attain equilibrium with the surrounding water level of kind of the broader groundwater table. And presumably in the coming months or years, we will see this continued rise of the water level as it seeks to attain an equilibrium with the water level measured kind of in the broader water table. A mile. Again, this well is about a mile away. How much could it rise? Well, we don't know with certainty, but we know that the water level at that well, about a mile away, is about 50 meters higher, about 160 feet higher than the current water level in the pond. So if we translate that to what the level is in Halema, this is it, and it shows that this pond, if it continues rising to that level, would get obviously quite a bit larger. Now Trish will talk a little more about chemistry.
So you haven't escaped the chemistry yet, there's more. So this top equation is the one that I showed before. That's producing that hydrogen sulfide, that rotten egg smell. But the same reaction can also produce native sulfur. So if we look back at those fumaroles that Matt was showing, there is actual yellow bright sulfur deposits forming where some of that gas is coming out. But what you see here is this commonality, this guy here. That's sulfuric acid. So when you have things like that being formed at a volcano, you can end up with an acid lake. So Kīlauea isn't the only lake or only volcano with this weird colored crater lake. There's a bunch of them found around the world in all sorts of different volcanoes. So Central America, Mexico, this is Corvin up in Alaska, Indonesia. There are a lot of these. And, you know, why do they look that color? What's going on with the chemistry? It's not the same color, it's not clear like you're drinking water. So what is happening? So to get at the chemistry, one of the first things you want to think about is pH, or how acidic that water could be. Because like I said, we're producing sulfuric acid with some of these gas reactions. So it's likely that that acid can end up in that lake water, but it doesn't have to. So this is a plot of pH, or acidity, of all sorts of different volcanic lakes around the world. And this is it's just frequency, just how many of them. So you can see there's 2 bumps here. It's not uniform across the board. So we have either this acid bunch here that sort of cluster around a pH of 1, or so neutral, like regular drinking water, is 7. So you can have volcanic lakes that are roughly neutral. We didn't know what we were dealing with. We can't just walk down to that lake, take a scoop, and send it off to the lab. So this is where drones came in. So some of you may have seen some of these videos on Facebook or Twitter from the USGS Volcanoes feed. The lake showed up in July. We didn't know if it was going to stick around. There were a lot of logistics with using a drone in a national park, and we had never dealt with water sampling with one. So we had to figure out a lot of logistics, but this is October 26th, so the lake was 3 months old, when we were finally able to actually use a drone, and in cooperation with the national park, you know, we had to do safety permits and things to make sure we were going about this the right way. But you can see, so this is a far out view, but this is our little hexacopter here, and there's this string with a special water sampler. I think it was 20 feet hanging off the bottom. I'll jump to the next video because it's got a better view. So it's a little hard to pick out. Here's the drone descending. Here's the line there's a sampler on the bottom. And you'll notice there's little flags in different neon colors. There's a yellow one there. The other ones are a little hard to see. That was so the pilot of the drone could use the downward looking camera and see which flags were under the water surface, so he knew how far down he was and how close he was to the water surface. So there's a drone. So we can still see the little yellow flag. So that one didn't get all the way in the water, but there's pink going under. So we ended up getting a sample from about 10 to 12 feet down below the surface of the water. And we got about 750 milliliters, so not quite a liter. It's sort of a bottle of wine volume. You don't want to drink this though. So there's our water sample, successful, up and out from the lake. It still had to come all the way back to us on the crater edge, which is not trivial. It's heavier at that point, so it's harder to steer the drone. And I'll jump to one more video, which has a really cool point of view. So this is the camera on the drone itself. So it's looking down. We're hovering over the surface. There's our little neon flags on the line as it descends. I think some of the other videos were a little sped up. This one is slower. The suspense is building. So like I said, this is sort of what our drone operator, who was a pilot that we were cooperating with from the Department of the Interior Office of Aviation Services. There's our splash. And actually, when people saw this video online, they had questions about what happened to the flags. So they thought it melted or dissolved. It just got wet and stuck to the rope. So you can see the pink one there. Yeah, it's just wet. Once it's back up in the air, you can see it flopping around again. But yeah, there's the water coming back out. So like I said, we were happy with that, almost a success, but we still had to get it back to us, which we finally did. So we did a couple measurements right in the field to measure pH as soon as we got the water. And then for more, you know, we've never had a water lake here before. We don't have a lab meant for doing all the advanced chemical analysis on the water. So we ended up sending the water away to our colleagues in California to do the more advanced analysis in the lab. But if we jump back to this pH or acidity plot, like I said, most volcanic lakes in the world are going to be in this neutral cluster or this sort of really acidic cluster. We are not. We're weirdly in the middle, which, you know, we had seen this plot. We were expecting, you know, we figured it was probably acid. We had a lot of sulfur gases. It was probably going to make that sulfuric acid and send it down this way, which it is trying to do. But the thing is, it's a new lake. The water's rising. All that acid water, or what would be more acidic water, it keeps encountering more and more new rocks to react with. So those rocks are sort of tempering that acidic tendency and pulling it back more toward a mild acid. So a pH of 4, it is an acid, but it's not going to melt your hand off or anything like that. Different foods and juices and things that you consume all the time are in that same range. The bottle of soda that I referenced before, that's more acidic than the lake. So it's not as acidic as we might have thought it would be. If it sticks around for a long time to the point where it reacts with enough of the rocks that it's only in contact with already reacted rocks, then we might start seeing that acid build up and dragging it more toward a more common, really hyperacidic pH. But we don't know how long that would take. We don't know, it may already be changing. And other things about that chemistry, so Matt showed some pictures of those weird colors, like it's not regular water. So if this is just some of the basics of the chemistry, there's our pH around 4. Other things that you notice, that's a whole lot of that sulfate. So that's coming from that sulfuric acid, which is coming from that SO2 that the water's dissolving. So that high level of that sulfate is showing that we have that dissolving of SO2 into the water, which is a process called scrubbing. And then they were able to determine that this mineral called gypsum or anhydrite is actually saturated in the water. So we have little solid bits of that mineral sort of suspended in the water or raining out of the water as a solid. So there are little bits of this solid gypsum or anhydrite in the water. And if that wasn't happening, this calcium number and this sulfate number would be even higher. So we're actually losing some of that sulfur to that solid phase. The other thing you notice is we have this really high number for magnesium. That's because Kilauea's rocks are really high in magnesium. So that reaction of the acid with the rocks is basically dissolving those rocks to some extent, and all that magnesium is ending up in the water as well. And then we have these weird colors. So this is a picture of a filter that the gross, weird yellow water was filtered through. And the filter ended up with this mustardy orange crust on it. And in some cases, you can actually do analysis on that solid material and figure out exactly what those minerals are. Unfortunately, that didn't quite work out. So we have some guesses as to what that might be based on the chemistry of the water, the chemistry of the rocks, and the colors. So it could be some minerals that are rich in that same sulfate, because we've got a lot of that, and iron. Minerals like jarosite or schwertmanite, which I had never heard of until we had this lake. And Matt alluded to this, that color's not static. So any volcanic lake can change color. So these are some examples from Indonesia. So Kīlauea Volcano, this is the only volcanic lake that I could find a picture of online that has a similar orangey rusty color as our lake currently does. But as you can see, at different times, that same lake at that volcano could be sort of greenish yellow or this orangey brown. Now they think, someone's hypothesis was that the orangey brown was related to it being a dry season, which it's currently not dry here, but our lake is still orange. So something's different about our lake. And then this is really cool. This is another volcano that has 3 different crater lakes, all in close proximity. And it's crazy. You can see at any given time, all 3 lakes are different colors, and then they change to different colors, and they're different from each other still. So unfortunately, I couldn't find any literature about the actual chemistry of these lakes, but I did find an example of a volcanic lake in Japan. So their color change is more subtle, but it is sort of in that yellowy, greeny range that our lake was originally. And so what they did is use a device called a colorimeter, which can actually look at the surface of the lake or anything and actually quantify the color and like the contributions of the red versus the green versus the blue into that ultimate single color. So they were able to get samples of their lake, measure the chemistry, and then compare it to that quantified color at any given time. So they were able to say, okay, the blue stuff, that's sulfur. So native sulfur, like I showed you in one of those equations, is depositing, and that the interaction of the light with that sulfur can make the water look bluer. But once you start getting different forms of iron interacting with the light in the lake water, you can head in a green direction or a yellowy orange direction. So they stuck mostly in this green to blue area. We are definitely in the yellow orangey range. So Matt actually is currently, we didn't buy one yet, but he's renting a colorimeter, and he just got to try it for the first time today because the clouds finally parted. So that is a tool that we're thinking about using in the future to try and quantify these color changes that we're seeing, because we have had color changes. So this is just about a week or so after the water was first noticed, and it's sort of greenish, maybe a little blue tinge in there. And then as time went on, we started getting yellow, especially in the middle. Then it was sort of a more uniform greeny yellow. This was just a couple days after we got the water sample via the drone, and you can start to see sort of a more orangey patch forming over here. And then it's gotten progressively more orange, rusty color. But like Matt said, you can still see these more greener tinges at the edge where we have that, what's probably that influx of the groundwater that hasn't yet reacted with as much volcanic gas. So, like I said, we got a water sample here just a couple days before this, and it was somewhere in the middle, so somewhere yellow colored sample. We're actually hoping in the next week or two, so we've been working with the Department of the Interior to get permission from them to do a sampling mission again. And now we're in the phase where we're working with the National Park to secure permission from them. But hopefully within the next week or two, we'll be able to get another water sampling mission done. And this time, because we know we have these different colors, we're gonna try and get more than one sample, try and maybe get one right at the edge of that greener color, and then something in the yellow range, and then from the darkest rusty brown, just to see how those different colors vary with the different chemistries, or if there's different chemistries. Maybe everything's playing a trick on us and there's really not that much of a chemical difference between the colors. But we're hoping that, like I said, in the next few weeks, we hope to have some more news on whether the chemistry has changed much, whether the pH has changed much. Because at other volcanoes around the world, some of those chemical changes can give indications about how much sulfur's coming out. Because like I said, we're measuring low sulfur emissions right now, but that's because a lot of it's ending up in the water. So we're trying to better quantify how much we're actually losing to the water by getting another water sample and looking at the chemistry of that. So now Matt's going to talk about some other aspects of, or implications of what this water lake may mean.
Okay, so the water pond is interesting, but it's also a potential concern, because when magma interacts with water, it can trigger explosive activity. And that's obviously would be a hazard at the summit, or potential hazard at the summit. And this happens at many volcanoes worldwide. These are two crater lakes that have had frequent explosive activity. Poas in Costa Rica and Ruapehu in New Zealand. So, this is obviously on our minds, the potential for explosive activity, in particular because Kīlauea has, there is precedent at Kīlauea they're in the geologic record, and there is a long history of explosions at the summit that have affected the entire summit region. This is the Keanakekoi explosive sequence that occurred in the 1500s to 1600s to 1700s. And some of these explosions are thought to have occurred or been triggered by magma rising up and interacting with water, groundwater or surface water. And so this is one of those units. So this gives you an idea. The deposits in the summit area are up to 11 meters thick. And that's the kind of the cumulative deposits from the 300 years of activity. But this is just one unit, Unit D, and you can see 10 centimeters of ash deposited. This is the golf course subdivision. So these larger scale explosions that have happened in the past at Kīlauea have the potential to affect areas outside of the caldera. So this is obviously on our minds and one of the concerns related to the presence of water at the summit. The difficult thing is that the exact processes that trigger this explosive activity, because this is long ago, there wasn't modern instrumentation to track this, the exact conditions that triggered that explosive activity are still not completely understood. Now, most likely, explosive activity in the future would be preceded by detectable precursors such as rapid inflation or increased seismicity. That indicates magma is rising. However, at crater lakes, there's always a small chance that small kind of steam blast or phreatic explosions can occur with little or no warning. But just the presence of water alone doesn't guarantee explosive activity. We know that there's an extensive water table at the summit, and we've had many previous eruptions, fissure eruptions, that presumably traveled through that water table. Fissure eruptions in the 70s and 80s, for instance, that did not trigger explosive activity. So there must be other factors, in addition to water, that controls whether an eruption is explosive or non-explosive. For instance, perhaps it relates also to the rate at which magma rises. Faster rising magma might leave less time to drive or boil off the surrounding water and lead to explosive activity, whereas slower rising magma might allow time to kind of boil off and have a non-explosive eruption. It's still not completely understood. Because of this concern for the potential of explosive hazard at the summit, we're continuing to keep a close eye on the summit. We have webcams. We are making routine measurements of the water level, because water level alone at other crater lakes has been a potential precursor to explosive activity. Abrupt changes in the water level. Thermal measurements, again, tracking the temperature of the water pond at other places has been a sign of changes in hazard. And of course, we're going out looking at just making routine visual observations, changes in the color, like Tricia talked about, at other volcanoes, at other crater lakes, have also been potential precursors to changes in activity, routine overflights. And Kīlauea has one of the kind of the densest geophysical monitoring networks of any volcano on Earth. So we have this existing network that we're, of course, always keeping an eye on. What's happening beneath the surface? Well, over the last year, we have inflation that began earlier in 2019. So, and this inflation rate is actually higher than what was happening in the years before 2018. And this basically makes sense. We had a large draining event in the summit magma chamber, and now magma is recharging that chamber. We also have elevated seismic activity at the summit, when you compare it to the years prior to 2018. And over the last 6 months or so, we kind of have this kind of occasional small swarms of tiny earthquakes. But overall, there's no detectable signs or obvious signs of imminent unrest or precursory activity that would lead to explosive activity in the near future. No signs of imminent unrest at the summit. We have this water pond. It's relatively stable. We have this slow and consistent rise in the water level. We have these minor, moderate changes in color. We have this inflation. This is indicating that the magma chamber is recharging, as we would expect. We know the magma is still relatively deep in the system. Tricia talked about the SO2 emissions and how some of that's complicated by the presence of the pond potentially absorbing some of that SO2. We have seismicity that's elevated compared to the kind of the pre-2018 levels, but it's not at an alarming level. So, this is Don Swanson, who's worked at the summit for many years, has said something along the lines that this is the most exciting period of activity at Kīlauea that he's seen in his career. Because we're obviously in a new era that we haven't seen in many years. So I think we're all interested to see what's next. And I have to show and share all of the future talks and activities that are going on with Volcano Awareness Month, and I'll just leave this here. And I think Janet is here, and she can provide more details on these events. There's more information on our website, and actually what I didn't mention is that obviously this is an exciting time on Kīlauea, and because things will eventually change, that I encourage everyone to keep an eye on our website and keep an eye on our updates. We have monthly updates about activity and regular updates, and that can be found here. So Tricia, on behalf of Tricia and myself, we want to thank you.